For changing forms of an equation involving exponentials or logarithms, we use the following change of form definition. X is equal to e to the y, then y is equal to ln x, natural log of x. X is equal a to the y is equal to log base a of x. This would be exponential form right here, and this is logarithmic form. Change the following equations from exponential form to logarithmic form, or vice versa. So you have 3 to the 4 is equal to 81. That's in exponential form. A to the y is equal to x. So in logarithmic form, we would write y is equal to log base a of x. So 4 is equal to log base 3 of 81. E to the 0 equals 1. This is in exponential form as well. E to the y equals x. So to put it in logarithmic form, y equals natural log of x. Log of 0.1 is equal to -1. This is in logarithmic form. Log base 10, if you see, if there's no base written, then it's base 10. Log base 10 of 0.1 is equal to -1. So in exponential form, that would be 10 to the power of -1 is equal to 0.1 or 1/10, which is true. Note that if f of x and g of x are inverse functions, then f of g of x is equal to x, and g of f of x is also equal to x. That's the definition of inverse functions. And we'll be using that for example 5. Example 4, since e to the 0 equals 1, natural log of 1 is equal to, we just did that one, so the natural log of 1 is equal to 0. And since e to the 1 is equal to e, then the natural log of e is 1. Because the natural exponential function and the natural logarithmic function are inverses, the natural log of e to the n is equal to e to the natural log of n, and that is equal to n. Definition of inverses. Use the inverse idea to simplify. So natural log of e to the n is equal to n. Natural log of e to the root 2 is equal to root 2. E to the natural log of 3x. Remember, e to the natural log, that's basic, those are inverse operations. So those are basically negating each other. So what we have here is 3x. 10 to the log of 2. This only can be simplified to be 2 if the base of the exponent matches the base of the log. And since the base of the log is not written, we know it's 10, therefore it matches, and that's equal to 2. Log base 2 of 2 to the x squared. Log base 2 of 2 are inverse operations, basically negating each other, which leaves us with our exponent x squared. Remember your properties of logarithms, that the natural log of a product can be turned into separate natural logs as a sum. The natural log of a quotient can be written as natural log of a minus natural log of b, and the natural log of a to the n is equal to n natural log of a, because natural log is undoing exponents, so your exponent pops to the front. Expand using logarithmic properties. So the natural log of a quotient is equal to the natural log of the numerator minus the natural log of the denominator. All right, that's expanded. For this one, I'm going to rewrite as natural log of, I'm going to write the root as a power because we do have a rule for powers here. To the 1/3. Now, when you have a power, you're taking the natural log of something to a power. That power pops down to the front and becomes your coefficient. So now you have 1/3 natural log x squared plus 1. Okay, natural log of x squared plus 1. Can I simplify that? Do I have a rule? The natural log of a sum? No. So that is as far as we can expand this. Condense into a single logarithm, for example, number 7. I see a -3 here. It is a coefficient, which means it needs to pop up and become the power for the x. But to save myself some steps, I'm going to rewrite the order of this because I know that when it's in the form of subtraction, I can easily turn it into the natural log of a quotient. First, we will use this property to bring the coefficient back up to a power. So this is natural log of y to the fifth minus natural log of x to the third. And now we can write them as a single logarithm, natural log of the quotient y to the fifth over x cubed. Please note that this is definitely not the same as this. The goal of condensing is to condense it into a single logarithm. The first thing I'm going to do is take any coefficient and turn it into a power. Natural log of x to the 1/2 plus natural log of x plus 1 minus natural log of y cubed. Now this 1/2, x to the 1/2, I'm going to rewrite that as a root. Natural log of root x, and now I can condense to write as one logarithm. When you are adding the natural log of something to the natural log of something, that becomes multiplication. Square root x plus 1 inside your single logarithm. And when you're subtracting, that means you're dividing by the argument in the log that is being subtracted. And this would be our single. To isolate x, like any other time, we're going to use inverse operations. So first I'm going to subtract this 6 on both sides. Y minus 6 is equal to e to the 2x minus 5. Now I need this exponent to now be a coefficient, but I can only do that if I'm taking the natural log of e to the 2x minus 5. And if I take the natural log of the right side of the equation, I also need to take the natural log of the left side. Yay! Natural log of e to the 2x minus 5 is simply 2x minus 5, and you can continue to isolate x from here. And you get 1/2 natural log of y minus 6 minus 5. What if you put that into the calculator? What do you get? For part B, we have two separate logarithms, and we need to condense them in order to use inverse operations. So log base 2 of, since we are subtracting these logs, we will write the arguments as a quotient. Now, the inverse operation of log base 2 of something is to put both sides of the equation as a power, with the base of that power being the same as the base of the log. So we want to put 2 to the power of the left side of the equation is equal to 2 to the power of the right side of the equation. And this is how that looks. Now 2 to the log base 2 of x over x minus 8 is x over x minus 8 equals 8. Let's get this quantity out of the denominator. And I'll distribute that. So x is 64 over 7. There is a formula for changing the base, since the only two logarithmic bases on your calculator are 10, which would be the log key, and e, which would be the natural log key. You will change the bases on your calculator in one of two ways. Log base a of x is equal to log of x over log of a, or log base a of x is equal to natural log of x over natural log of a. Use your calculator to find log base 7 of 112 to 3 or more decimal places. Log base 7 of 112, you can put this into your calculator as log of 112 divided by log of 7, or you can put it into your calculator as natural log 112 divided by the natural log of 7. Let's try both and see what we get. And I got the same answer for both of them, which was 2.425 rounded or 2.424 truncated. Find an exact value for x if 3 to the x plus 2 is equal to 6. Okay, x is in the exponent, and I want it to no longer be in the exponent, so the inverse operation of an exponential is a log. And the base of our exponent is 3, so the base of the log must be 3. And if we take the log base 3 of the left side, we also need to take log base 3 of the right side. Log base 3 of 3 to the x plus 2 is just x plus 2, and that's equal to log base 3 of 6. To isolate x, our final step is to subtract 2 on both sides, so x is equal to log base 3 of 6 minus 2. That's the exact value for x. And here they want us to use our calculator to find a decimal for your answer from part A to 3 or more decimal places. So you can use log or ln, just as long as you're using the change of base formula. Log base 3 of 6 is the same as natural log of 6 over natural log of 3 minus 2. And that's what I'll be putting in my calculator. Or you can use log. And I got negative 0.369.